All right, today we're going to learn about counting. So hopefully it'll be a quick and painless kind of lecture day. Suppose you attend your friend's wedding and at the reception you get to select your dinner. There are two choices of appetizer. What should my two appetizer choices be? You normally choose from soup and salad maybe? Three choices of entree. So what entrees could we have? Steak, fish, chicken, and three choices of dessert. So maybe the desserts are ice cream, pie, and cake. Obviously cake, it's a wedding. Okay, so the way you can think about this is like, if I choose soup, I could choose either steak or fish or chicken next. And if I choose steak, I could then choose ice cream or pie or cake. But I also have the same three choices if I chose soup and then fish. I'd also have the same three choices if I chose soup and then chicken. In fact, if I started off with a salad, I would have then the choice of steak, fish, or chicken, and then for each of these choices, I still have the three choices of dessert. So in total, how many different meals can I create from this kind of decision tree? 18. And hopefully you can see the reasoning why here. If I have two choices of appetizer and three choices of entree and three choices of dessert, I multiply 2 times 3 times 3 to get 18 because every time I make a decision, I multiply the number of options I have. So the answer here is 18. Suppose you are a traveling salesman and you need to drive to 5 different cities this week to meet clients. Since you're responsible for making your own schedule, you can put those 5 cities in any order you like. How many different ways can you put 5 cities in order?
Would it be 25?
Yeah. So you're thinking like 5 times 5? Sounds could be a natural way to think about it. 25 is not the exact answer. Anybody else have any ideas for how I could figure out how many different ways can I put these cities in order? Like, I could travel to Kansas City first, and then Tulsa, and then, I don't know, what's another city around here? Chicago, and then St. Louis, and then Denver. Or I could travel to Denver first, and then St. Louis, and then Chicago, right? How many different ways can I put 5 cities in order? So the correct way to think about this, I think, is there's going to be a first city I travel to, and then there's going to be a second city I travel to, and then a third and fourth and fifth city that we travel to. As I'm going about, I first have to decide what is the first city I'm going to travel to, and how many choices do I have? We've got 5 different choices, right? After I travel to that first city and I'm thinking to myself, well, what city should I go to next for my second visit? How many choices do I have to choose from then? I think I heard it very softly. Somebody said 4. If I travel to 2 cities and I'm thinking about where I'm going to travel for my third city to visit, how many choices do I have? 3. And then for the fourth city? And do I have any choice at all? Now, after I've traveled to 4 cities, I don't get a choice in where my 5th city is going to be. So once again, I have a decision tree, but this time the number of options available to me at each choice are going down. And so the correct answer is 5 times 4 times 3 times 2 times 1, which is 120. So I've got 120 different ways where I could reorder the cities that I visit. So this is what I mean by counting. When I say we're learning to count today, we're counting the number of different ways I can permute cities or the number of different meals I can have at a wedding. Here's some vocabulary words for you. A permutation of a set is the arrangement of the elements of the set in order. In the last problem we just worked, we had a set of 5 cities. So each city would be an element in the set. And the permutation is deciding what order am I going to visit those cities in. And it turned out that there was 120 permutations of a set of 5 elements. The factorial is a function that we use a little exclamation mark for. A factorial is a function where you take the number and you multiply by every positive integer going down to 1. Or honestly, like I wrote it, you don't need to multiply by 1 because multiplying by 1 doesn't change anything. So like 5 factorial is 5 times 4 times 3 times 2 times 1 if you like. Okay. So this has a special name in math because it appears a lot, not just in counting problems like this one, but it also appears, if you take more math classes, we find other ways to use it. So we decided it was important enough to give it a name. And the answer to any permutation problem is a factorial. So if you're judging a chili cook-off and there's 10 competitors, and imagine a ranked choice voting system where you have to rank all 10 of these chilies on your scorecard before you turn it in, how many different ways could you do that? How many unique ballots could you submit to the voting system? This would be a permutation of a set of 10 chilies. So, and you don't have to tell me the exact number, right? But Sarah, how would I determine how many different ways I can put 10 chilies in order? Okay, so like we just talked about, this is a factorial problem. The answer is 10 factorial, which is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Because it's a permutation. And in Desmos, if you're taking a test and you want the factorial, you just type in 10 factorial, right? So everybody can do this super easy on test day. 10 factorial is 3,628,800. Different ways you can write 10 names in order. Very big number. Okay, this is a different type of question, so I want you to think about it before you answer here. But it says, your toddler is playing with blocks, and there are 6 unique blocks. The blocks are magenta and red and blue, green, orange, and purple. Your toddler's tiny hands can only hold 2 at a time, so 1 in each hand, right? Not Okay, so there's my 6 blocks. How many different ways can your toddler choose 2 out of the 6 to hold?
times 12 because you have like the 6 blocks, but you can hold 2 at a time. So you need to choose one, and then you know, wouldn't it be 6 times 5? It'd be okay. I'm thinking out loud.
Yeah.
So like, because he picks one out of 6, and that's one of them. But then he picks one out of the 5 left. So it'd be 6 times 5, and then it would be that's 30. 30 times 6.
Okay, so I like what you're saying with the 6 times 5, because you choose 1 out of 6, and then you choose another 1 out of 5. Where did you get the, why would you multiply by 6 again, though?
Oh, no, you wouldn't.
You're really close to the right answer.
Yeah.
Right? Does that make sense? You're saying with your left hand, you choose 1 out of the 6, and with the right hand, you choose 1 out of the remaining 5. So 6 times 5 is 30. The only thing that we can do to make your answer a little bit better is to say, well, if I'm just wondering what 2 out of the 6 we chose, then the order doesn't matter. It doesn't matter if I pick up the red first and then the blue, or if I pick the blue and then the red. And so there will be 2 copies of that when I do 6 times 5. There will be a red, blue, and then a blue, red. So to really get the correct answer, I should take 6 times 5 and then divide by 2, right? Because the order doesn't matter. So 6 times 5 divided by 2 is 15, and that's actually the right answer. You can verify this really easily if you get your hands out and you count them. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 different ways that you can hold 2 out of the 6 blocks. Very good. I'll give you another question. This is going to be a little bit harder to think about, though. You go to compete in a golf tournament where there's 12 total golfers. They divide up the golfers into groups of 4 that go through the course together. The first group of 4 is selected at random. How many different ways can they choose 4 out of the 12 golfers? So it's kind of like choosing 2 out of 6 blocks, but these numbers are larger, and so that makes it a little bit more of a mind bender to think all the way through. How many different ways can we choose 4 out of 12? Excuse me. And here's the way I would suggest you think about a problem like this. Imagine I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The first thing you might consider is how many permutations, or in other words, how many ways can I put these golfers in order? And the answer to this is 12 factorial, right? If I'm just concerned about putting them in order from left to right. Step number 2 is we place a partition between the first 4 and the last 8. So after I've placed these 12 golfers in order, I can divide them now into the first group of 4 and the 8 golfers that don't belong to the first group of 4, right? And then after I place down this partition, I think to myself, well, I don't care about the order of the first 4. And this is a little bit tricky to think about, but now that I've placed the 12 golfers in order, I've considered all the different ways we can do that, and I split them into 4 and 8. remember, I'm just counting how many different ways we can choose 4 out of 12. I don't really care if this is Joe and this is Bob, or if this is Bob and this is Joe. I don't care if these 4 golfers change the order they're lined up in. But whenever I counted 12 factorial, the lot of these permutations have exactly the same 4 starting golfers, but they just appear in a different order. Well, how many copies do I have with the same 4 starting golfers, just in a different order? I have 4 factorial copies of each starting set, right? Where everything else about the permutation is exactly the same, except the first 4 golfers appear in a different order. Well, I don't care what order they appear in. And so we need to divide by 4 factorial in order to eliminate those redundant copies that are essentially the same for our purposes. Step number 4, and this is the last part, I don't care about the order of the last 8 golfers. So then we divide by 8 factorial. And we're dividing by 8 factorial because, again, if I'm counting the number of permutations that are exactly the same, with exactly the same first 4 golfers, 1, 2, 3, 4, and the same last 8 golfers, but where the last 8 golfers might appear in a different order from one another, there are 8 factorial of those permutations that for our purposes are the same, but we don't want to double count them, right? We don't want to redundantly count these extra ones. So we are dividing by 8 factorial in order to adjust for that, to compensate for that. So now, if I have started with 12 factorial and divided by 4 factorial for the order of the first 4, and divided by 8 factorial for the last few, consider that 12 factorial would be 12 times 11 times 10 times 9 times 8 factorial. And 4 factorial is 4 times 3 times 2. I could write this. Everybody follow along? And then these 8 factorials are going to cancel, top and bottom. Do you have a question?
So yeah, with that, could you just like technically keep going down the line all the way, like, and that's what factorial is, like you just go 12 times 11 times 10 times 9 times 8 times 7, like keep going.
Yeah. So 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah. But the reason I wrote it like this is because I wanted you to notice I can cancel out the 8 factorial in the numerator and denominator. I can just cancel those factors since they...
You could technically do that with the 4 factorial too if you kept going on the 12. It's easier and more efficient to do it with the bigger factorial, but you could technically do it with the 4 too.
Yes, that's true. Mm-hmm. So then I think to myself, 12 divided by 4 is 3. And then I've got 11 from the numerator. 10 divided by 2 is 5, and 9 divided by 3 is 3. And you don't have to do this, but then the last step here is to just go to Desmos and type in, what is 3 times 11 times 5 times 3? $495. So the answer to the question, you've got 12 golfers. How many ways can you choose 4 out of 12 to be in the first group? The answer is there's 495 different ways to choose 4 out of 12. And this formula we came up with it works in general. Like what I mean to say is, if I go back to my toddler playing with blocks, this time this is choosing 2 out of 6. So I would take 6 factorial divided by 2 factorial divided by 4 factorial, right? because I have 2 blocks and then a partition and 4 more blocks, and I don't care about the order of the 2, I don't care about the order of the 4. Well, this would be 6 times 5 times 4 factorial. 2 factorial is the same thing as 2. The 4 factorials cancel. 6 times 5 is 30. 30 divided by 2 is 15. Okay, so more vocabulary words for you. What we've been doing right now is called a combination. A combination of a set is a subset of its elements in no particular order. So choosing 4 golfers out of the total 12, 4 is the subset, 12 is the set. And I don't care about the order. That's called a combination. The binomial coefficient is the way we calculate this. In the binomial coefficient, we write it with a number n sort of floating above a number k. Don't write a horizontal bar. It's not a fraction. This is not a fraction. But this is called a binomial coefficient. And the way you calculate the binomial coefficient is you take n factorial, where n is the size of your set. You divide by k factorial, where k is the size of your subset you're choosing. And you also divide by n minus k factorial, which is the number of elements from the set that don't get to be in your subset. So like in our golfer example, this was 12 factorial divided by 4 factorial divided by 8 factorial. If you see this and you're reading it out loud, the way you read this out loud is you say the words n choose k whenever you see the binomial coefficient. So let's do one more of these and then we'll move on to something else. You're eating at Genghis Grill and there's 8 types of protein. Only 3 can go into your wok bowl. How many different ways can you choose 3 out of the 8 proteins, Martina?
We do 8. What is it called? The explanation point was actually called?
Factorial.
Yeah, so we do 8 factorial.
8 factorial. That's part of it.
And then divided by 3 factorial.
Divided by 3 factorial.
And in parentheses, 8 factorial minus 3 factorial.
Yeah. In parentheses, it's 8 minus 3, and then the factorial is outside the parentheses. So we do the subtraction first. We do 8 minus 3 first. But yeah, this is the binomial coefficient. This is 8 choose 3. And 8 choose 3 is calculated using, of course, 8 factorial, which is 8 times 7 times 6 times 5 factorial. 3 factorial in the denominator is 3 times 2. 8 minus 3 is 5 factorial. And so then you would say, well, my 5 factorials cancel. And this becomes something like 8 times 7 times 6 divided by 3 times 2. 3 times 2 is 6. What's 8 times 7? 56. So it turns out at Genghis Grill there's 56 different ways you can choose your proteins. Very good. All right, this is a similar kind of question. It's building on the questions we've asked before, but a little bit different. It says, while visiting your nephew, he asks you, what are your top 3 favorite Power Rangers in order? So think about this. Let me count. 1, 2, 3, 4, 5, 6, 7. There's 7 total Power Rangers. We're asked to pick our top 3, and it matters in what order we place them. So think about this for a minute. How many different ways could you respond to the question? So this question has two parts. In the first part, we have to take our set of 7 and choose 3. So we're going to have 7 choose 3 as the number of different ways I can pick 3 Power Rangers to be my favorite Power Rangers. But the question goes further than that, because this combination is not in order. It's asking how many different ways can I also place these 3 in order? Well, once I've chosen 3 of them, I can put them in order by then multiplying by 3 factorial, because 3 factorial is the number of different ways I can reorder a set of 3 elements. It's the number of permutations of my subset. So this is the answer. We just have to simplify it a little bit. Obviously, 7 choose 3 is 7 factorial divided by 3 factorial. And then this would be 7 minus 3, or 4 factorial. In this type of question, where you get a combination and then it's reordered, this is called a partial permutation. In this type of partial permutation question, you always end up canceling out 1 factorial from the numerator and the same one from the denominator. So this becomes 7 factorial divided by 4 factorial. And then you cancel the 4 factorials, and this is 7 times 6 times 5. It's 210. So let me describe the situation one more time. The reason we said 7 choose 3, this binomial coefficient, we read it out loud by saying 7 choose 3, is because I've got 7 Power Rangers and I have to choose 3 of them. Okay? So that's the number of different ways I can choose 3 out of 7. I multiply times 3 factorial because that is the number of different ways I can take a set with 3 elements and then permute them in different ways. So that's why I'm multiplying by 3 factorial, is because I'm supposed to place them in order. This, where it says 7 factorial divided by 3 factorial divided by 4 factorial, that is how we calculate this binomial coefficient. That's just part of the formula. And I noticed that this 3 factorial cancels with that 3 factorial. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Or another way to write that would be 7 times 6 times 5 times 4 factorial. So then the 4 factorials cancel, and then you get your answer. Are we good? Questions? Okay, awesome. Like I said, this type of question is called a partial permutation. A partial permutation is the ordered arrangement of a subset of its elements. So like where we had a subset of 3 elements from a set of 7 elements, it ended up being this, because some of the factorials cancel out, right? If I have a situation like this, this is the binomial coefficient, but we're also multiplying by the k factorials. The k factorials cancel, and then you get that formula.
What was the other permutation called?
Just a permutation. If you're permuting the entire set, it's a permutation.
So,
If you permute a subset, it's a partial, yeah.
yeah, so you only use the partial permutation when the order of the things matter.
Yes,
Okay.
that's right. If the order doesn't matter, it's just called a combination. Yeah. Just a couple more question types. Well, let me let you do this one for practice. Very similar to the Power Rangers question, okay? This one says, your uncle has no hobbies aside from watching football. He's trying to make conversation, so he asks, Rank your top 5 favorite NFL quarterbacks. Suppose you're only familiar with the 32 starting quarterbacks. How many ways can you respond to his question? This is a partial permutation. Of a subset with size k equals 5 from a set with size n equals 32. It's a really big number. Huge number even. And so the formula for partial permutation says we're going to take n factorial divided by n minus k factorial. So in other words, 32 factorial divided by 27 factorial. And that's 32 times 31 times 30 times 29 times 28 times 27 factorial. So you're right, really big number, but we have our phone and we have Desmos on a test, so you can type in 32 times 31 times 30 times 29 times 28. And the answer is 24,165,120.
I have a question.
Mhm.
Why did we not multiply it by 5 factorial?
Good question.
Because isn't it a random system?
It is a good question. Yep. So, yeah, the deal is whenever we have a combination where we're choosing 5 out of 32, we do this part for the binomial coefficient. And then when we place them in order, we multiply by the 5 factorial, right? It's in order to take that set of 5 and permute them in order. So every single time you have a partial permutation, this k factorial from the binomial coefficient that's down here in the denominator cancels out the k factorial in the numerator that we get from permuting it.
Oh, okay.
And so that's how we ended up with this formula. And this is the formula that I wrote down here.
So it's included, we're just...
Yeah, it's included, it just cancels. Yeah, and like with the Power Rangers question, I sort of worked this out more explicitly where we had the binomial coefficient, that's right here, and then the number of permutations right here. And then we said, oh, well, those cancel in this case too. So you can write it or you can skip it. It's up to you. Okay, this is a different problem type. So read this one carefully. It says you have 3 identical white t-shirts. There's one. And you have 2 identical red t-shirts. And you've got 2 identical blue t-shirts. Meaning that you can't tell your red t-shirts apart, you can't tell your blue t-shirts apart, and you can't tell your white t-shirts apart. For a total of 7, imagine that you only wear exactly 1 t-shirt per day. And the question is asking, how many different ways can you wear all of these t-shirts during the course of a week?
You said you can't tell them apart. But for the purpose of this problem, are they different?
No.
No? They're all the same? Okay.
So if I wear a white shirt on Monday and Tuesday and Wednesday, I don't know which white shirt I wore on what day. It's completely meaningless to try to number these or anything like that for the purpose of counting, right? It doesn't make a distinct choice if you reorder the white shirts or the red shirts or the blue shirts. You might have an answer. Okay, so let's discuss. Step one is we imagine for a moment that they are distinct. And we can tell them apart. Then, in that case, there would be how many different ways to wear 7 distinct shirts in 7 days? 7 factorial. Yeah, that would just be a permutation of the whole set. So if they had distinct shirts, then there would be 7 factorial different ways to wear these. But number 2 says, I don't care about the order of white shirts. I don't care about the order of red shirts. And lastly, I don't care about the order of blue shirts. So considering all of this, we take our 7 factorial different permutations, but we are going to divide by 3 factorial. I'm dividing by 3 factorial because for any given permutation in the set of 7 factorial different permutations, there are 3 factorial permutations that are exactly the same that only differ in the order of the white shirts. But those are all essentially the same thing for us because we can't tell the white shirts apart. So we're dividing by 3 factorial to eliminate that redundancy in the way that we're counting. Then we're also going to divide by 2 factorial because, again, among this set of 7 factorial different permutations, there's 2 factorial of them that are exactly the same, but differ only in the order of the red shirts. And I don't care. I can't tell the difference between those 2 permutations. So we divide by 2 factorial to eliminate the redundancy in the way that we've counted. And then lastly, I divide by another 2 factorial for the blue shirts. So in the numerator is the size of our overall set, and in the denominator, we divide by the size of each subset, and every number gets a factorial. So this is, of course, 7 times 6 times 5 times 4 times 3 factorial divided by 3 factorial, and 2 factorial is just the number 2, right? 2 times 1, if you will. And then that 3 factorials cancel. 2 times 2 cancels with the 4, and 7 times 6 times 5 is 210. So if you don't like doing mental math, just open up your Desmos calculator and type in the numbers, right? I don't care if you use the Desmos calculator or if you use your brain, either way. The point of this problem is just that you know how to set up the solution. And you can get the solution even if you have to use Desmos.
Is the number with the factorial just that number times the 1? Like you said, 2 factorial is just 2.
2 factorial is just 2, but 3 factorial is 3 times 2. And 4 factorial is 4 times 3 times 2. And yeah, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2. Yep. Okay. Questions? Everybody's good? This is called a partition. The partition of a set is what it looks like to sort its elements into multiple subsets. The number of partitions of k subsets with sizes n1, n2, n3, and k from a set of size n is this. So in the numerator, right, this is the overall size of the set. And in the denominator, you could have 2 subsets or 3 subsets or 4 subsets, right? It depends on the problem, how many subsets you have. But these numbers are the sizes of their subsets. Like in this case, I had my 7 days of the week, and I was sorting the days of the week into subsets that represented what color t-shirt I was going to wear that day. So there was 3 subsets because there was 3 different colors of t-shirt, and they had sizes 3, 2, and 2. Okay, a couple more pages of notes. We're almost there. So try to stay awake a little bit longer. And it's Friday. I'm ready for the weekend. Although I still have another class after this. So you are designing a stylish tile border in your bathroom. On hand, you have 4 identical brown tiles, 5 identical blue tiles, and 6 identical green tiles. Without buying any more tiles, how many different ways can you place these tiles in order? You do?
15 exclamation mark over 5 exclamation mark times 6 exclamation mark times 4 exclamation mark.
Yeah, that's it. Very good. So this is, again, this type of problem is called a partition. And the idea is I've got 15 places where I can put a tile down. And all of these 15 places, I'm sorting them into one of 3 subsets, either the brown or the blue or the green subset. And the number of ways I can do that is going to be 15 factorial divided by 4 factorial, 5 factorial, 6 factorial. So 15 is the size of my set, and then 4, 5, and 6 are the sizes of my subsets. And then we, of course, have to do the math, or maybe Desmos can do the math, I don't know. Maybe if you get super lazy, you go over here and you just try it out and you say, what would it look like to just type in 15 factorial divided by 4 factorial, 5 factorial, 6 factorial? It can do it. So 630,630. It's kind of a nice number in a way. A lot of different ways you can put those tiles in order. You are designing a stylish tile border in your bathroom. Oh my gosh, this looks very familiar. The difference in this problem is if your neighbor finds herself in the same situation and randomly selects a configuration of tiles, what is the probability that you and your neighbor end up with the same tiles arrangement? Does anybody want to take a guess?
Wouldn't you just multiply 630,000 630 times 2, and then like it'd be 1 over that number?
You're onto something with 1 over that number, right? But
Because like it'd be 1 over 630,000 times 1 over 600. Or not, because it's like both 1 and
You're really close to understanding this, but you don't need to multiply by 2, and you don't need to multiply or square it, right? The answer is just 1 divided by 630,630. Because you've got to have some kind of arrangement, right? Like your neighbor is going to have an arrangement that represents 1 out of 630,630. And so whenever you place your tiles, what's the probability that you get exactly the same one? It's 1 out of this number. Does that make sense? Your neighbor's tile pattern is fixed. We don't know what it is, but it is fixed as one of those options. And when you put your tiles down, this is the chance that yours matches that one out of the number of total possibilities.
So the other one is already
The desired outcome out of the total number of possible outcomes.
that as they're both setting it, what is the probability that they both play the same thing, not with it already being set? Like with what we were talking about with the die rolls.
Wait, but that would still be the same thing, though.
It is the same.
It just depends how you look on it. Because if you like, it's almost like, oh, wait. Because it, I can't get the words out. It makes sense.
Yeah. Even if you're both laying tiles at the same time, as long as you don't see each other and you're not copying each other's work, then the probability is 1 out of 630,630. Yeah. So this is how counting relates to probabilities. As if you can count the number of total possible outcomes, then you can relate it back to a theoretical probability where you've got like some number of desired events divided by some number of total events. And this is the reason why counting questions like this appear in the probability chapter of most textbooks. Okay, last question for today. You open a new deck of playing cards and randomly shuffle the deck over and over again until they're shuffled really, really well. What is the probability that the cards are now in the same order in which they came? So you're supposed to get out a deck of 52 playing cards, and you shuffle and you shuffle and you shuffle and you shuffle, and you spend hours shuffling and changing the order of these cards, and then you stop. And you've shuffled them so much, no one can keep track of where the cards went, right? What's the probability that now they're sitting in exactly that order? Cards 1 through 52.
1 out of 52 factorial?
Yep. This probability would be 1 out of 52 factorial. Because again, the question is, how many different permutations of 52 cards are there? That'd be 52 factorial. And there's only one outcome. There's only one permutation that has this exact order. And so the answer is 1 divided by 52 factorial, which is obviously super small. A couple of fun facts before you leave. I've heard it said before that 52 factorial is a really big number. In fact, 52 factorial is a number larger than the number of atoms in the observable universe. Huge number. Not just big, it's unimaginably large. And to that end, every single time you shuffle a deck of playing cards, it's likely that's the first time the cards have ever been placed in the order at any point in history from anybody's deck of cards, right? Like every single time you sit down and you shuffle a deck of playing cards, you're picking 1 out of 52 factorial possible permutations. What are the chances that anybody in history has ever done that? It's like super, super duper small, right? So yeah, shuffle a deck of playing cards and that'll be the first time anybody's ever put those cards in that order. Probably. Yeah, not guaranteed, but probably, odds are on your side.